Fluid Mechanics by Laureano Andrade Vicente, MD 21, and the MCAT Disciples. If you end up liking this lecture, you really ought to check out some of the other work that I've done in the MCAT prep industry, because I do a hell of a job teaching MCAT prep topics, and I love to be able to help you get a great score on the MCAT. So visit us at MCATdisciples.com if you so happen to enjoy this lecture. I think this is going to be a fun lecture. Here's our AAMC topic list. This is all we're going to go through. I'm going to go through everything here, although I'm not really going to focus on Poiseuille's law, because Poiseuille's law, we're going to focus more on the physics correlates to the human body cardiovascular system lectures. And there I'm going to deal with more about real fluids and, the blood vessels and the vasculature, all that kind of stuff. But for now, we'll just focus on the basic physics. We won't get so complicated. As an introduction, a fluid is a liquid or gas. So, for example, the air is a fluid. The orange juice that you're drinking this morning is a fluid. I know it's kind of counterintuitive to think it's gas as a fluid, but that's what they are. I know, like, in common parlance, we use fluid to refer to liquid, but fluid is a liquid or gas in any other language. And some important considerations to think about when you're thinking about a fluid is the concept of, particularly in water, the difference between temporal resistive forces and permanent resistive forces. An example of temporal resistive forces would be if you were to put your hand in a pool, for example, and you move your hand left and right, you'll notice that there are some resistive forces to your movement. But those resistive forces are called temporal because the reality is those resistive forces are being generated from the intermolecular attraction between the water molecules and the fluid, if we're dealing with water. But those are impermanent because on a tonic basis, on a normal basis, even if that water looks like it's not moving, the water molecules are moving and are kind of moving past one another and breaking and reforming hydrogen bonds. And so since that's happening, since they're always moving, those hydrogen bonds can only provide a temporal resistance, an impermanent resistance, because they're always moving. And they're always moving because the water has a temperature associated with it. If something has a temperature associated with it, that means it has kinetic energy. And that's how you know it's moving. Even if it doesn't look like, even if it's called a static fluid, you still have water molecules moving left and right. Anyway, the water can also generate a permanent resistive force, or any other fluid, but that fluid can only generate that force at its surface. At its surface. Because at its surface, there's an interface between the fluid and whatever else its environment is in. And it turned out, for example, in the case of water, you'll have a lot of resistive force being generated there, because of the fact that the water molecules are here, right? And these water molecules are relatively constrained to moving. In the case of the surface here, these water molecules can't move upward just because the force of gravity is keeping them down here. And in the case of any other sidewall, you have this fluid here hitting up against the sidewall, but it really can't move it unless it's a really weak wall, right? And so these puppies are generating a permanent resistive force outward, and I've drawn this in here, at any one of their given surfaces. And as it'll turn out, the pressure at any one of these surfaces, ignoring the change in depth, is going to be the same. A critical consideration when dealing with fluids is density. And we need to deal with density because of the fact that we normally don't know what the mass of a fluid is. I mean, you can measure it if the fluid is small enough, but generally speaking, we don't know what the mass is. But we usually know what the volume is, and so we can use the property of density, which is an intensive property, a property that depends on only the fluid in question and not any number of the fluid, to determine perhaps the mass of the fluid or whatever other value we need to use or get. And so we'll introduce you into the terms of extensive and intensive properties. We may have said this before, but this will just be a review then. Extensive properties depend on the size or number of the system. For example, the volume, right? The volume, you calculate the volume by multiplying, if you're using a square, or rather a cube of base times height times length, right? And so obviously that depends on the size or number of the system. Moles, again, obvious. Mass, obvious. Intensive properties are independent on the number or size of the system. For example, pressure and temperature. Okay, and here's where people lose their gondol minds. Okay, they say, okay, PV equals nRT. And they say, well, if I increase N, I'm going to increase P. I'm going to say, well, do you know what's being held constant? And then you're going to say, no. because I know if you increase N, for example, the pressure, if you don't know the volume is not changing, then if you increase N, you increase V, right? Unless the volume is being held constant somehow, and then maybe pressure can change. But what you need to know and make sure that you need to know what's being held constant. So it turns out under normal conditions, if you increase N, you're just going to increase the volume of the gas, right? Because the ideal gas at standard temperature and pressure takes up 22.4 liters. So under normal conditions, that's what's going to happen. And the temperature and the pressure won't change. Okay. So if you divide an extensive property by another extensive property, you get an intensive property, a property that doesn't depend on the number or size of a system, and that's what density is for us, where M is the mass and V is the volume, and that has units then of kilograms per meter cubed, which is equal to grams per liter. You should know this, memorize this, and you should know the density of some common compounds like water. Density of water is equal to 1,000 kilograms per meter cubed. And so again, just to we've already done this in another lecture, but just to kind of emphasize here what density is. Density is just how much stuff you have in any given volume. So for example, if we draw this square here, and obviously this is area, this is the volume, but if you multiply by h here, you can make a little cube and get the volume. If we draw the same size square, less stuff. Draw the same size square, less stuff. So that's what density is telling you, right? How much stuff in mass, in kilograms, that you have per unit volume. All right. So why don't we just go through an example? What happens to the density of a fluid if you compress it? What do you think the answer to that is? All right. Well, density is mass per unit volume. If you compress it, you're decreasing the volume. Then clearly, then the density increases. So the density increases. Alright, introduction of fluid, specific gravity. Oh, and just to go back here, usually the fluids are generally incompressible. Not fluids, rather. Liquids are generally incompressible. Water is generally incompressible. And we usually take liquids rather, to be incompressible. Gases are very compressible, and you already know that from PV equals nRT. And then solids are generally incompressible, right? Just to... Okay. So there's also a term that we use in physics here called specific gravity, which kind of gives us an understanding of how heavy something is. Because density, okay, you say, all right, this thing has a density of, I don't know, 5,000 kilograms per meters cubed. Does that mean anything to you? Do you have some, inherent understanding, some kind of practical understanding of what that means? No, probably not, right? And so specific gravity is the term created to kind of give us a kind of more practical understanding of what it means when something has a certain density. So specific gravity is just the density of some substance over the density of water. The specific gravity of Mercury, for example, is 13.6. And so what does that mean, and what is that telling us? That means that Mercury is 13.6 times heavier than water of any given volume. So if you had equal volumes of Mercury and water, that Mercury would be 13.6 times as heavy. So this is kind of a pictorial representation of that. You'll notice that if we have 13.6 buckets of water, that'll be equal to 1 bucket of mercury. All right. So if something has a specific gravity greater than 1, the substance weight is heavier than water. If it's equal to 1, it's equal to water in weight. And if it has a specific gravity less than 1, the substance weight is lighter than water. Not too bad, not too bad. So sometimes you'll get density, sometimes you'll be given specific gravity in question, then you just have to be able to interchange between the two, knowing that what the density of water is. So here's another example. A solid container holds air, which has a density of 1.3 kilograms per meter cubed at 0 degrees Celsius. If the temperature is increased to 273 degrees Celsius, what is the new density of air? What is the new density of air? Well, if you had density as mass per unit volume, did this change? No. It's a solid. It's a solid container. It's a solid container. What does that mean? If you have a solid container, that means the volume is not going to change, no matter what you do inside of there. And if the volume isn't changing, the mass isn't changing, this thing stays the same. Now, it's critical that that's a solid, because if that wasn't a solid container, then potentially the density could have changed here. Potentially. I mean, we'd have to see the specifics of the question. But if it's a solid container, you know the volume is not changing. And so that right there finishes the question. The density is still 1.3 kilograms per meter cubed. And again, you can rearrange the ideal gas law to determine how the density relates to the rest of the values here. And here you would just say, well, the temperature increases, so the density decreases. But that's just not the case. That's just not the case because there's something in here that you're not considering, which is the volume change, because you've gotten rid of it by canceling it out. But the volume here is not changing. And so this density, mass per unit volume, wouldn't be changing. Something here would increase to equalize the increase on the bottom there. Perhaps pressure, probably pressure. No, it would be pressure. There's nothing else that can be changing. So this is not right. Again, what's being held constant is important. An ice cube with a specific gravity of 0.9 is placed into a container that is exactly the same size as the ice cube. If the ice melts, which of the following is true? Okay, so two things here that are important. If you don't know already that the density of water is going to increase as it goes from solid to liquid. Again, this is very exceptional. Water is the only compound that I know of that does this. Usually it's the opposite. If you didn't know that already, you've been told a specific gravity. And you know the specific gravity is just the density of the object over the density of water. So immediately you know, in this water in liquid form, immediately you know that the density of that ice cube was smaller than the density of water, right? But if you didn't know that, you could have memorized this from the past, that the density increases as you go from solid to liquid in water. And so that just means that the density is increasing, so the volume is decreasing. So the volume, the water in this case, will actually take up only 90% of the container there, right? Just from the density change. So very interesting is that when you take water, put a water bottle in the freezer, and you freeze it, the water actually expands. It actually from the transition from liquid to ice, the volume actually increases, so the density decreases, and it may just break open the water bottle. All right, another example. A machine has a power of 2 times 10 to the 3. Power is joules per second. Remember that. If when operating at this power, it can lift 100 caskets of water to a height of 1 meter in 20 seconds, how long would it take to lift 100 of the same size caskets filled with paraffin, which has a specific gravity of 0.8? Again, the specific gravity of 0.8 just means that it's 80% as heavy as water for a given volume. And in this case of this question, we have the same volumes for each of the caskets. So it should take 80% of the time, no? So you just 20 seconds that it took for the water times 0.8, 80%, 16 seconds of the time it'll take. And this is just kind of a free body diagram showing kind of how the time it takes to go up is related to the mass. We can move on to static fluids. So static fluids are non-moving fluids. And again, just to get past this right now, when we say a fluid is static, we mean that on a macroscopic level it's not moving. But clearly, if any fluid has a temperature associated with it, it has the molecules have a kinetic energy associated with it. And they're moving in all kind of random directions. But the directions, again, are random. They're not in any uniform motion. Okay? So that's what we mean by static fluid. And due to those molecules moving up in random molecular motion and colliding with one another, they generate what's called then a fluid pressure. It's the pressure exerted on an object submerged in a fluid as a result of a molecular collision. Now let's get one thing straight right now. If a tree falls in a forest and nobody hears it, I don't know I don't even know what the freaking saying is. There's pressure there even when there's not an object there. Okay, you don't have to have an object in the fluid for there to be a pressure there. The pressure is there all the time. That pressure can be calculated via force over area, right? And this is for static fluids. Now you use this equation for static fluid. This equation does not apply to moving fluids. That's critical. The units are going to be in pascals, or PA, and that is the SI unit. That's what the unit you'll get if you use meters and you use newtons and you plug in your numbers. You're going to get out pascals. You can interconvert between pascals and Torr and millimeters of mercury and 1 atm just with the following here. And the pascals is can be approximated to 10 to the 6 pascals, so 101 101,000 can be approximated as 10 to the 6th, and that's the number you'll use. Now, there are other ways that you can calculate the pressure. And actually, before I move on to the next way you can calculate the pressure. So, for example, if you know the force at which these little molecules here were hitting up on the sidewall of this box, and you know how many were hitting up against it, then you can calculate the force there, and you can take the area of this side of the box, which would just be base times the height here. This is meant to be h. And then you can calculate the area, and then that would be the force, right? So you can do something like that if you were given that kind of information. But there are other ways to calculate the pressure of this fluid. You'll notice here that we have two heights here written down. We have H1 and H2 right here. And the pressure generated at these two different heights are actually different. So that you can talk about fluid pressure and say the pressure of the fluid is this, right? And that would be ignoring any changes in depth in the fluid itself. And other times you want to be more specific and say, well, the fluid pressure here is lower than the fluid pressure here. And why do you think that is? Well, let's look at the equation. P equals to rho GH, where density is rho is the density of the fluid, G is 10 meters per second squared, and H is the depth. Clearly, all of this is fluid, right? All this water is fluid molecules in it, blah, 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 blah. And the deeper you go, the more fluid you have on top of you. So the larger pressure you're going to feel at any given point, right? And so the pressure, and this is getting ugly. So the pressure at height 2, the depth 2 rather, H2, the pressure is higher here than it is here. And that's actually going to be critical to our conversation about the buoyant force later on. We won't go there yet. So, pressure is equal to rho GH. So you can determine the pressure based on the density of the fluid, how heavy the fluid is, times gravity, times the height, and that'll get you units of pascals. So again, you realize that this equation is the way it is because the depth that you're at will indicate to you how much fluid you have on top of you, which of course can generate a pressure, a heavier pressure than having less fluid on top of you. And the density is in here because you want to know how heavy those fluid molecules are that are generating that pressure on you. Obviously, a heavier molecule can generate more force when hitting you or what have you. This is known as the gauge pressure. This is just the pressure, a difference in pressure really, or the extra pressure due to the fluid that you're in. Right? And so if you want to consider the absolute pressure, which is this pressure here, P, and we'll have some labels here, you have to add the atmospheric pressure. So you have to add the pressure due to all of these air molecules on top of this fluid that are also generating a pressure. So pressure is a scalar. It has no direction, by the way. And then again, here we have the gauge pressure again being shown here. The additional pressure due to the fluid in question. All that is just the pressure generated by the fluid in question. The liquid in this case, the water in this case. So like anything else in physics, we just got to do a bunch of problems to get ourselves comfortable. Before we do that, we have one more thing to show here. Alright, I mentioned earlier that air is a fluid. And as you know, as you go higher in altitude, people say the oxygen tension drops. And it does. The partial pressure of oxygen drops. And that's just due to the fact that as you go higher up, you have less fluid molecules on top of you. You have less air molecules on top of you. So you generate less of a pressure. The height, the depth is higher from the surface than to on top of a mountain, for example. And here's what I want to make a big, big emphasis on, and I probably have emphasized it before. When you go higher up in altitude, it is not that there's a decrease in oxygen concentration. There's a decrease in the partial pressure of oxygen, not due to the change in moles of oxygen. That stays the same. But because the partial pressure is decreased. Because the actual total pressure is decreased. The absolute pressure is decreased. And you know that that'll make it harder to breathe because now you have a decreased pressure gradient for water, for air to flow down and get transferred into the body and bind to hemoglobin. Does anyone remember, maybe actually not remember, but does anyone know the physiological response to going higher up in altitude? In order to get more oxygen to tissue beds in the conditions of low pressure, the body is going to start to increase the production of red blood cells and hemoglobin. So you become polycythemic. It happens at the bone marrow. Anyway, so what do you do with the situation where you have multiple fluids on top of a point and you want to know what the pressure is at the bottom of that container, for example? Well, you just take the rho GH of each fluid, you take the density of each fluid, and you calculate the pressure by adding them up. I think this is reasonable. Finally, we've come to the concept of Pascal's principle, which says that the pressure applied to any point in an enclosed incompressible fluid will be distributed undiminished throughout that fluid. Now, this is, of course, at a certain depth. So the equal pressures here are at equal depth. And it has to be the same fluid, right? And it has to be enclosed, otherwise the pressure would just kind of dissipate outward. So again, if you're at a given depth, the pressure is going to be the same no matter where you're here, you're at this weird place, or you're at this weird place here. The pressure there is going to be the same. Now, it's not going to be the same if you move out here, because that's a different fluid. Because this point here does not have this water on top of it. It only has air. And so in order to calculate this thing, you'd have to calculate the depth that you're at here up to, for example, the depth of the top of the atmosphere. And that would be the pressure. And that's not going to be the same as this, because this is a different fluid. This has a different density than air. Right? And so this won't be the same as what's out here. But the rest of these in this fluid are going to be the same. Here's just a ramification of Pascal's principle. Again, Pascal's principle says that if you generate a pressure at one point in a fluid, that pressure is going to be distributed undiminished to the rest of the fluid. And that's critical. Well, not critical. Well, it is critical, but it's useful in generating lift, particularly in the use of hydraulic lift. So if you ever had to change your car's tire, you bring out one of those things that you kind of step on and it ultimately lifts up the car. I guess it's the hydraulic lift. You step on it, you step on it, you step on it, and you say, wow, I'm lifting up a really heavy car. I mean, a car is usually like 5,000 kilograms or something. And so that's hydraulic lift at work. So again, by Pascal's principle, the pressure at 1 is equal to the pressure at 2, although the forces are different. Okay? And so you can generate with a small force a very large force on the other end. Just kind of manipulating this. Because think about this now. If you make this area really small, you can increase force 2. If you make this force really big, which again you're not really good at, you can increase this. And if you increase the area of A2, you can increase force 2. So you can imagine you can generate a really large force from a really small force initially just through Pascal's principle. The other thing to remember is that in this, the work is also constant, right? The work doing at left is also the work that you do on the right here. And so this is also an equation that you can use and you may need to use in questions relating to Pascal's principle. Pascal's principle just says that the pressure generated at one point on a fluid or exerted on one side of a fluid is going to be that pressure is going to be spread out undiminished to the rest of the fluid. Alright, so here is just an example dealing with Pascal's principle. The car shown in the diagram weighs 1,500 kilograms. So it seems I exaggerated a little bit by saying 5,000 in the last slide, but that's okay. The area of piston 1 is 0.05 meters squared, while the area of piston 2 is 5 meters squared. If the car is accelerating uniformly at a rate of 5 meters per second squared, how much force was initially used at piston 1? The pistons are weightless and frictionless. Okay, so here's what we know here. We already have a free body diagram drawn for us. We know that the car is accelerating uniformly at a rate of 5 meters per second squared, and we know that net force is equal to ma. So we know that F2 minus mg has to be equal to ma. We know what the acceleration is, we know what mg is, so we can use that to calculate force 2, which is just plugging in our numbers here. We're plugging in right here for the mass. This is the mass of the car, this is the acceleration of the car, plus the mass of the car again, times gravity. So it's not too bad. We do our math, we rearrange a little bit. We find that F2 is equal to 2 times 10 to the 3 newtons. We know that F1 over A1 is equal to F2 over A2. So we know that F1 is equal to F2 over A2 times A1. So we can start plugging in numbers here. We can say 2 times 10 to the 3 over A2, which is 5, multiplied by A1, which is 5 times 10 to the negative 2. So our 5's cancel out here. When we end up with is going to be 2 times 10 to the 1, or 20 newtons as our answer. So now you can see again that you can generate a lot of force with just a little bit of force on one end, and all that is really due to Pascal's principle, just the pressure being spread out undiminished from one point in the fluid to another. Another example. During your vacation in Isla Verde, Puerto Rico, you take a dive into the water to a depth of 40 meters, what would be the gauge compressor compared to the surface at 1 atmosphere? All right, so we're looking for gauge pressure here. What's gauge pressure? We know P is equal to, that's the absolute pressure, rho GH, or the total pressure, or the real pressure, plus PO. PO, the atmospheric pressure. We want to know the gauge pressure, so we just want to know P minus PO, which is equal to rho GH. So why don't we just calculate that? Here's our little free body diagram. You're at a depth 40 meters down. You know what the height is. It's just 40 meters. You don't have to change it because that's the SI units. You plug in your number. There's your density of water, which is 10 to the 3 kilograms per meter cubed, times the gravity, times the height, which is 4 times 10 to the 1. You have a gauge pressure of 4 times 10 to the 5th Pascal. So that's just the pressure due to the water alone. This much water. That's what the gauge pressure is, right? And then if you want the absolute pressure, the actual pressure you're feeling down there, you also have to do the atmospheric pressure PO, which in this case is 1 atmosphere. So, or, 10 to the 6th Pascal. So you'd have to add that to the gauge pressure to get the actual pressure, the absolute pressure. But that's not what we want this time. Here's another example. Here we have a bunch of fluid at different densities given by density 1, density 2, density 3, density 4, this little figure here to the right. So the first question is, this is a closed system at rest, so everything has kind of settled out. The first question is, which fluid has the largest density? We really haven't talked about this yet, but I think you probably know already that the more dense you are, the more likely you are to sink. And if you are denser than the fluid you are in, you are going to sink, unless you react with the fluid or something. So the fluid with the largest density is going to be the one at the bottom, which is the purple fluid. The next question, at which labeled point is the pressure the highest? At which labeled point is the pressure? So we have B, we have A, we have C, we have D. I already told you that the deeper you are, the more pressure you're going to have. The less deep you are, the less pressure you're going to have. So the deepest that we have here is going to be B, right? Because B has the most fluid on top of it. Look at this. Boom, boom. It's got the brown one, it's got the blue one, it's got the whatever color this is, light brown. It doesn't matter, again, because Pascal's principle said that the pressure here is going to be equal to the pressure here. So it doesn't matter that it's kind of off to the left here. This point here, B, is feeling the same amount of pressure as it is at this point here. Okay? So that's going to be the highest pressure, regardless of where it is in the fluid. And then that's what Pascal's principle is all about. So don't be afraid. For example, I just want to make a point here. This point A here, in this little weird kind of outshoot of this, I guess, stone thing that's holding the fluid, that pressure there is equal to the pressure here. Doesn't matter that it doesn't look like the brown fluid is on top of the blue fluid here, because that pressure being generated by this light brown fluid is being transmitted all the way down to that point here. Okay, because that's Pascal's principle. Then finally, what is the pressure at point A if we have all these densities here? So this is just a calculation, a simple calculation. So we want the pressure at point A. So you just have to add up the density times the gravity times height of this fluid plus the density plus the gravity times height of this fluid, and use the appropriate heights to determine the answer here. The atmospheric pressure is 0 because of the fact that it's a closed off system. So here are the numbers. You plug those in, and you ultimately find that the pressure is 12.5 times 10 to the 4 pascals. Oh, still have the eraser on. Pascals. Not too bad, I think. And that's pretty much the types of questions they intercede for static fluid. But we'll keep going. Fluid has been added to each of these containers to a depth of 4 meters. Which shape has the highest pressure at the bottom of the container? So which shape has the highest pressure? And these are all at the same depth, more or less. They all have fluid added to a container 4 meters. And they're all closed off, by the way, to the atmosphere. This is closed. And the answer is they all have the same pressure. The shape of the container does not affect the pressure. What affects the pressure is going to be the atmospheric pressure plus the gauge pressure, the additional pressure due to the fluid. You don't see container here. The container is not in this equation, so that's not going to affect the pressure. So please get that right on the test. Anyway, here's the simple mercury barometer. And we've already gone through this, so I'm going to go through this kind of quickly. There's something, not special, but there's something specific about the simple mercury barometer that I really want to discuss here. So the atmospheric pressure, a barometer is a vacuumed out tube being placed into a little container of fluid, and that fluid is pushed up into the tube, not due to capillary action, but due to the actual atmospheric pressure pushing the fluid in. So the pressure here generates the pressure here, and because Pascal's principle says that the pressure is distributed undiminished, it also puts up a pressure here, and that pushes the fluid up, and then the fluid will go up to a height based on how dense that fluid is, and essentially the weight of gravity pushing it down. Measuring pressure, a normal atmospheric pressure will raise a column of mercury up 760 millimeters, hence the unit 760 millimeters of mercury. So we say 1 atm is equal to 760 millimeters of mercury. Nothing special here. You can still use this equation to calculate the pressure, but in this case the PO is 0 because this is the vacuum. So this is what we're taking as PO. PO is usually atmospheric pressure, but it's really just the pressure that you take as the environmental pressure. So in this case, we're actually trying to, with a barometer, we're trying to determine atmospheric pressure, which is in this case this big P. Okay, so that's kind of one of the nuances that I wanted to mention here about the barometer. And then the other thing that I just want to explain here again is that, okay, you have this pressure generating, pushing this fluid up here, and as time progresses, the fluid starts to travel up the column, and it starts to get more and more about the weight of gravity, because as the fluid goes up, it's not like gravity is changing, but you have more mass up in the tube here, and hence the force of gravity increases. And there'll be a point where the force of gravity is equal to the force that's pushing the fluid up, and hence the pressures are going to be the same. And so the pressure, for example, here is equal to the pressure here. The pressure here is equal to the pressure here. The pressure here is equal to the pressure here. And I know some of you are going to say, Laureano, you just told me in the last, a few slides ago, that if it's a different fluid, it's going to be a different pressure. And that's why I'm going through this. The barometer is made to determine what the pressure at any given depth outside of the barometer is. So the pressure here is meant to be the pressure here, even though it's a different fluid, because this is what the machine, the tool was made for. Okay, so try not to mess those things up there. And just to make sure you get it, again, you've seen this before, but pressure at A is 0 because it's a vacuum. Pressure at B is 380 torr because this is 380 millimeters up. Pressure at C is the same because, not because they're the same or different fluids, but because this is, the barometer is made to measure at any given depth what is the depth of the atmospheric pressure surrounding it. So D is 780 torr because 450 plus 380 is the height above it, and that's the actual atmospheric pressure, or the pressure at the surface of the Earth in this case. And then F is 830 because you're at the distances up here. Okay. If you're given a barometer not made of mercury, you have to use the appropriate density and SI units to calculate pressure. Not bad, right? You just use this equation with, and again, remembering that PO for the barometer is going to be 0, and the pressure is just this pressure. That's where people get messed up, if they start thinking that PO is like the atmospheric pressure that they're supposed to calculate, but this is 0. And the rho GH is not the gauge pressure, it's the actual pressure, it's the atmospheric pressure. In the case of the barometer. Here's a manometer. So a manometer also measures pressure. So the barometer measures pressure just like the manometer does, but the barometer is supposed to be specifically for just measuring atmospheric pressure. Now, there are baroreceptors in the aortic and carotid body of the human body, and so the term is kind of loosely associated with only being used for atmospheric pressure, because clearly we have adopted that name in biology. But they just both measure pressure. That's almost the same thing, but the manometer is typically U-shaped as it's shown here. So we're going to do a question with a manometer. We have the density of the gas in this figure is 1.3 kilograms per meter cubed, and the blue fluid is water. If the height difference is 10 centimeters, what is the pressure of the gas? So first off, just from intuition, knowledge of how things work, is that if the pressure of this gas is higher than the pressure of the atmosphere, which is out here, then it's going to push that fluid up here, so the height would be higher on this side and lower on this side. And if this atmospheric pressure was higher than the gas pressure, then it'd be pushing inward, right? You just know that just from your understanding. But you also know that wherever you have a pressure differential, you have movement of fluid, right? We haven't covered fluid mechanics yet, but you probably know that just from me emphasizing it in different lectures. And just to be clear about two things here, if there's a pressure gradient, a fluid will flow, assuming that it has a pathway to flow down. If it doesn't have a pathway to flow down, or there's too much resistance on that pathway, it won't flow, right? So let's get that clear. And the second thing to make clear here is that, again, in this situation, we're not accounting for any changes in depth of the gas here. You know, we're not saying, well, there's a difference in pressure here and here in the gas, because clearly there is going to be a pressure difference there, but that's not the pressure we're interested in. We're just interested, generally speaking, in the pressure of this gas, how much force is being generated on any given piece of area in this little pipe here. Yeah? Okay. Anyway, you want to know what the pressure of the gas is? Well, the pressure of the gas would be P minus PO plus rho WGH. And now the gauge pressure is the pressure we're interested in. We're not interested in atmospheric pressure. So the gauge pressure is what we're interested in. We're not interested in atmospheric. So it's just P minus PO. Now, you could plop in rho GH, and that will get you your answer, which is 10 to the 3 pascals. That's the pressure. That's the added pressure from the gas alone. Not too bad, huh? All right, my friends, we'll move on to objects and fluids. So there's some geometry you should know that'll be helpful in dealing with the kind of questions you'll run into with static fluid objects and fluids. So you should know the area of a cube or rectangle. Area base times height, volume is going to be base times height times the width. This whole thing of meters cubed comes from the fact that this is meters, and this is meters. So you multiply those three, you got meters cubed. Okay. You should know the area of a circle or sphere. The area is pi r squared, and the volume is 4/3 pi r cubed. Worth memorizing for a sphere. Triangle, you should just know area is 1/2 base times height. And then the cylinder, you don't have to memorize this at all. I'm just introducing it to you. Do not memorize this. It's just in case you want to, but I don't think you need to. You usually get dimensions in as follows: length times width times height. Appreciate that this is arbitrary most of the time. It really, what's length and width and height can sometimes mean nothing, or they can sometimes mean something. But generally speaking, they can oftentimes be arbitrary because you just change the way you're holding the box, and the length and the width and the height changes. Generally, the apostrophe, the double apostrophe, just mean that there's inches, and then one apostrophe means feet. You don't have to be able to convert from feet and inches to meters. In the MCAT, you'll probably get centimeters or meters or millimeters, but you won't get feet or inches because that's not SI units. And again, it's arbitrary what you call what sometimes. Like for a cube, there is no length, width, and height because all the sides are the same length. Moving on. This is an image you've seen before. Now, you know how to calculate pressure already. You say pressure is equal to rho GH. And you know, since it's pressure is the function of depth, that the pressure here, for example, at this depth, is going to be higher than the pressure here at this depth, just based on this. So you know that the pressure gradient here. And if there's a pressure gradient, what's going to happen? Then they're going to flow down the pressure gradient, assuming they have a pathway to flow. In this case, there is a pathway to flow. So you know that there's some force there that's pushing this upward, and that force is called the buoyant force. And you know the pressure, because you know pressure is equal to rho GH, and the difference in height of this object gives you the buoyant force. And the other reason why you know there has to be a force here is if this object isn't moving, there has to be, and the forces somehow have to balance for this object to not be moving in the fluid, because they always have force of gravity working on you. And so that buoyant force is what's going to counteract that if this thing isn't moving. Anyway, you know what the delta P is. You know what the pressure gradient is. So they can use that to calculate what the buoyant force is, because the pressure is just force over area. In this case, the force is the buoyant force. So we can equate the buoyant force to rho GH. We can multiply both sides by the area. And now what we have there is area times height, which is what? That gets you units of meters cubed or volume. So we can plug in the volume to ultimately have a functional form of the buoyant force. This is the equation that you're most likely going to be using, where the buoyant force is equal to the density of the fluid, the volume of the fluid displaced, times gravity. Now, this is where a lot of people get tripped up. Sometimes there's a relationship between the volume of fluid displaced and the volume of the object, And that volume can sometimes be equal to the volume of the object, or it'll be equal to the volume of the object submerged. And you'll have to decipher when and where it is appropriate to use the volume of the object. And we'll go through how that you do that shortly. Anyway, that's the buoyant force there. Again, the buoyant force is the upward force exerted on an object in a fluid, whether floating, sunk, or submerged. And these are the two different equations that we have for the buoyant force. Now, you know that the buoyant force is also equal to, if you kind of flesh out what density means, you can cancel out the volumes of fluid that are in this equation and find out the buoyant force is equal to the mass of the fluid times gravity. Well, that's what Archimedes' principle says. Archimedes' principle says the buoyant force is equal in magnitude to the weight of the fluid displaced. So what did that mean? What did that mean? Archimedes' principle, the buoyant force is equal in magnitude to the weight of the displaced fluid. That means that if you have a force buoyant of 50 newtons, for example, and you take the volume of fluid that was displaced, which in this case is equal to the volume of the object that took the place of the fluid, and you take that volume and you weigh it on a scale, that scale is going to read 5 kilograms, which multiplied by gravity, 10 meters per second squared, is going to get you 50 newtons. So that's what that means. That's what Archimedes' principle means. And there's other ramifications of Archimedes' principle, which we're actually going to go through via questions. But the point of the matter is the weight of the fluid is equal to the weight of the buoyant force. So here's an example about Archimedes' principle. A hunk of pure gold is obtained, as well as a crown made of an unknown metal, both of equal mass. If the crown is also made of pure gold, should they displace the same amount of water or a different amount? Well, they should displace the same amount. Here's why. The volume of object under the water is equal to the volume of fluid displaced. Now, clearly, this statement is important. It's not just the volume of the object. It's the volume of the object underwater. And that's equal to the volume of the fluid displaced. And if that's the case, they have the same mass, and they have the same volume displaced, they have the same density, they're the same compound. So that's gold. And that's how Archimedes. So Archimedes was a scientist way back when who was asked by a king to determine whether or not the gold crown he received from his jeweler was real or not. And through a series of experiments, he found out that the volume of the object under the water is equal to the volume of fluid displaced, and hence the weights are equal, and hence if you have a compound that is the same mass as another compound and they're the same compound, they should also have equal volumes of water displaced. Moving on here. This is the slide that just wants to kind of represent to you the effect of percent submersion and the volume of displaced fluid on the buoyant force and how those two things relate. So why don't we write the force of the buoyant force here as rho Vg, where this is the fluid. This is the fluid. So this, remember I mentioned to you that there's a relationship between the volume of fluid displaced and the object. And sometimes the volume of fluid displaced is equal to the volume of the object. But when the object is not fully submerged, that is not true. When the object is not fully submerged, the volume of fluid displaced is equal to the percent submersion of the object times the volume of the object. So the strongest force buoyancy that you're going to have is going to be when the object is fully submerged, because then the volume of the object is going to be 100%, and that's going to displace all the fluid that it can ever displace, and hence have the strongest buoyant force it can ever have. But as it's less and less submerged, for example here, where it's only partially submerged here, the buoyant force is not that strong, because if you look at how to calculate the buoyant force, it's A times delta H, that's volume, it's not as high as it could be. I think you should deal with this and just look at this figure and kind of understand that. The magnitude of the buoyant force is limited by, in part, the percent submersion determined by density and the dimension of the object submerged. All these are really determined by density, not just the percent submersion, because the density is determined by, well, the dimension of the object. Anyway, there's another term that we have to kind of deal with, which is center of buoyancy. It's not something that you'll probably see, but you might see it, so it's worth mentioning. Here is an object that is made of half wood and half styrofoam, and right at the center there is the center of buoyancy. The center of buoyancy is always the symmetric center of the object. So the buoyant force will always be acting this way. However, that is not always coinciding with the center of mass. The center of mass, right, in a symmetric object would be the center. But in an object that is unsymmetric, the center of mass is going to be wherever the most mass is, right? And so the center of mass in this system, where the styrofoam is essentially weightless, we assume this is weightless or very light, that the center of mass is over here. And again, that doesn't coincide with buoyancy. So this can generate a torque. You can imagine the force of gravity going down this way, and the center of buoyancy going up this way, the force of buoyancy, and that would generate a torque on this object, such as the styrofoam would be up in the air and the wood would be down. And that's probably something you've seen if you ever played with a floaty or a buoy in the ocean or whatever. So moving right along here, we're going to move on to the three major situations to consider, which is the partially submerged object, the submerged object, and the sunken object. These different situations are the situations that you might see on the MCAT, and each one of these kind of have a little nuance associated with them. So we'll start off with the partially submerged object. As it says, this is a floating or partially submerged object. An object will float if the density of that object is less than the density of the fluid, because again, the density is essentially the weight, telling you at a given volume how much weight something has, or how much mass something has. And the ratio of the two densities will tell you the fraction submerged. So the density of the object over the density of the fluid is equal to fraction submerged. If this fluid is water, then that specific gravity tells you the fraction submerged. Okay, so we'll do an example. If you know the percent submerged and you know the volume or dimensions of the object, you can calculate your variables of interest. So, say an object is 20% submerged. That means that if the fluid is water, that's specific gravity. But you can say the force buoyant is equal to rho v fluid gravity. So again, the volume of fluid displaced in this case is equal to 20% of the volume of the object. And that's your buoyant force that you'd calculate. And since this object, if this object isn't sinking any more than it is, you know that the force of buoyant is equal to mg. So now you know the mass of the object as well, if you for some reason you needed that. So hopefully that works for you. That's not too bad, is it? Okay, let's do an example. A rubber duck is sitting in a bathtub of water with 1/3 of its body submerged in water. How much does the 2 meters cubed duck weigh outside of water? First off, that's a big duck, but anyway. How much does it weigh outside of water? So, okay, here's our little diagram that we should draw. The first step is to draw this diagram. Obviously, you'd probably just want to draw a box, not a duck. And you know that the force of, if this duck is not moving, you know the forces are going to balance each other out. So the force of gravity downward, and then you have the buoyant force upward, and those should be equal to one another. So we can say the force of gravity, mg, is equal to the buoyant force, or rho fluid times v fluid times gravity. So what is the volume of fluid displaced? That's like the big question here. Well, the volume of fluid displaced is just going to be the volume of the object times the fraction submerged. That's how much volume is being kicked out of that water by having that duck in there. That's equal to mg. So we can plug in our value just to find what mg is, which is our density of the fluid times the volume of the object times the fraction submerged, which is 1/3 times 10, the gravity, which is equal to 0.66 times 10 to the 4 newtons. And you would probably have to change that to 6.6 times 10 to the, I made this bigger, so I have to make this smaller, newtons. Okay, muchachos, we're going to move on to the next question here. If an object has a mass of 250 grams and a volume of 1 liter, what percentage of it will be found above water? So one careful thing here is to read carefully. This says above water, not submerged. So we already have the density. We're given that in the question. We have 250 grams per liter, which is equal to 250 kilograms per meters cubed, which is equal to the density of the object. Now we just calculate the specific gravity of this compound, which is 25%, just 250 over the density of water, which is 1,000 kilograms per meter cubed, which is equal to 0.250, which is equal to 25% if you multiply by 100. So that's the percent underwater, so the percent above it is 75%. Not too bad. We can move on then to the submerged object. The submerged object is an object that is not necessarily at the bottom of the ocean, for example, the bottom of the container, but it just isn't moving in the fluid. It's just submerged, it's under the water, but it isn't moving wherever you put it. It's not going to move. So an object will submerge if the density of the object is equal to the density of the fluid. So let's be clear about something. When I say submerged, I'm referring to a specific situation where the density of the object is equal to the density of the fluid. Clearly, a sunken object, an object that's all the way at the bottom of the container, is submerged, but I'm just using submerged as a way to define this situation. The ratio of the two densities tell you the fraction submerged, and if they're equal, the thing is 100% submerged, right? It's not necessarily sunk, and you're going to see why I'm making such a distinction here. So here's the free body diagram. You have mass of gravity downward. If this thing is not moving, the forces have to be equal. Net force has to be 0. So a force of buoyant upward has to be equal to mg in this case. Again, if you know your percent submerged and you know the volume or dimension of the object, you can calculate your variables of interest. Clearly, I need to proofread this more. Say an object is fully submerged. Then you say force of buoyant is equal to rho v fluid g. Then that's the fluid displaced. And since the object is fully submerged, the volume of the object is equal to the volume of fluid displaced. So we can say force buoyant is equal to rho fluid v object times gravity. In this case. So just to emphasize the point here about the specific gravity being equal to 1. So if your density is equal to the fluid density that you're in, you don't move. Wherever you're placed in that fluid, assuming it's a fully submerged position, you don't move. You just stay there. So if I were to put this object here, it would move, it would sink, and once it's sunk to this position right under the water, it won't move anymore. So that's what happens when you have a density equal to the density of the fluid you're in. The object with the density equal to the fluid density will be submerged and stays where it is placed in a static fluid. And then finally, the sunken object. Alright, an object will sink if the density of the object is greater than the density of the fluid. Surprise, surprise. And the ratio tells you the fraction submerged, so if it's greater than 1, you're sunk. Again, here's our force diagram here. Okay, now here's the thing. Again, it's not moving, right? So the forces have to balance. What do you know about when forces are hitting up against the surface? What are they always there? What's always there? The contact force, right? The equal and opposite force being generated by the floor or what have you from the mass touching or contacting the floor. That's the normal force. And of course, in this situation, you also have the buoyant force. And we know that these have to equal out. So we say in the case of the sunken object that the force buoyant plus the contact force and normal force is equal to mg. Now in this case, the normal force is not equal to mg because you have two forces going in this direction and just one this way. And so if it's not moving, these have to be equal. So clearly the normal force isn't the same magnitude as the force of gravity. I know, it's new to you, but that just has to do with the fact that, well, you have another force going on in the upward direction that you've never had before. Again, same really deal here. If you know your percent submerged, you can figure out your variables if you know the dimension of the object. So if an object is sunk, you say rho fluid is equal to v fluid times g, and since the volume displaced is equal to the volume of the object that displaced the fluid, in this case, because the object is fully submerged, we can say this. And we can also say that the force of gravity minus the buoyant force is equal to the normal force, which is equal to the apparent weight loss. So what does that mean? Well, the apparent weight, really. What does that mean? That means that if I were to put a weight scale right here under this object, it would not read the same as it would in the air. And that's because the buoyant force is removing some of the object's weight. And it just so happened that then the force of gravity minus the buoyant force, because the contact force is the only thing left, that's equal to the apparent weight. Hopefully that makes sense. Then finally, you can say that the density of the fluid over the density of the object, notice these two things are flip-flopped, is a shortcut that you can use to define the apparent weight loss. So how much weight was lost? Or the buoyant force, essentially, is what you're calculating there. So, that's that. Again, the way I remember this little shortcut here is I just remember that the fluid is on top when the object is sunken, or all the fluid is on top of the sunken object. But again, that's just like a shortcut to figure out a value that you're interested in. Okay, so an example. A cylindrical hollow object is floating on the surface of water. This object has a mass of 500 grams and is floating such that 4 centimeters of its height is submerged on the surface of water, while 12 centimeters of its height is above the water. How much mercury in milliliters would need to be poured into this cylindrical object in order for it to be completely submerged, where the density of mercury is 13.6 grams per centimeter cubed? Okay, so what we have here is essentially we're being asked how much mass do we have to add into this object at a given volume for it to go underwater. So let's draw a little diagram here. We have 4 centimeters under the water, 12 centimeters above the water. So that information there tells us actually the percent submerged. Hopefully you know, or not, maybe if you don't know, now you know, that you can use the height of an object underwater to determine how much volume is submerged, because the height is related to the volume. So the percent submerged is 4 over 16. I'm getting 16 by doing 12 plus 4 because that's the total height of the object. So 1/4 is the simplified version, hence 0.25 is the percent submerged. Now we can use that information to determine the density of this cylindrical object here by just multiplying by the density of water, and that gives us the density of the object of 250 kilograms per meter cubed. Now you know something will be completely submerged if the density of the object is equal to the density of the fluid it's in. In this case, we want it to be equal to the density of water. So we need to add 750 kilograms of mercury for it to sink, rather be completely submerged underwater. So we can calculate that by using the density of mercury to determine how much mercury in volume we need to sink it, and then we can convert that to milliliters to determine that 55 milliliters of mercury is needed to sink this object. Now notice that milliliters of mercury is not adding to the volume of the object, because we're just pouring that into the object. We're not actually changing the volume of the object. Okay. Another example. Hanging from a scale by a massless thread is a 5 kilogram sphere that is totally submerged in a water bath. If the reading on the scale is 30 newtons, calculate the radius of the sphere. And you can leave that in the cube root form. You don't have to finish the calculation. Here is the diagram. You have this massless thread holding on to the 5 kilogram sphere here. And that the scale is reading 30 newtons. So here's the forces acting on this ball. You've got the force of gravity, which is equal to 50 newtons. You've got the force of the tension on the string, the tension force, which is 30 newtons. And then you have the buoyant force, which is what we're interested in calculating, because the buoyant force is going to get us to the volume of the object, because the volume of the object is equal to the volume of fluid displaced. So we say force of gravity is equal to force of tension plus the buoyant force. Subtract those two, you get the buoyant force. And since we know what those two are, we know the buoyant force is 20 newtons. And we calculate then the density, the buoyant force. We say the buoyant force is equal to rho of the water times the volume of fluid displaced times gravity, which is equal to the volume of the object, which in the case of a sphere is 4/3 pi r cubed. And then you can solve for the radius, which is equal to this. Not too bad. So another example. There's a 100 kilogram iron anchor with a density of 8 grams per centimeters cubed at the bottom of the ocean. Attached to the anchor by a massless string is a 1 kilogram briefcase containing pterogen crystals. The briefcase has the following dimensions: 0.5 x 0.5 x 0.2 meters with the tension in the string. So the trick to doing these questions, this one in particular, is making sure you're only looking at one object and you're only drawing the forces acting on that particular object. You can draw forces acting on the other object, but they're just darn right going to confuse you. So you really just want to write the forces acting on one particular object. So in this case, I'm going to choose the briefcase, because the briefcase we have enough information to calculate the buoyant force on. So we draw a little ocean, we draw an anchor at the bottom, and attached by a string is that briefcase. So the forces acting on the briefcase is the force of gravity downward, which is just equal to 10 newtons. We have the tension force by the string going downward, and then upward we have the buoyant force, and we can calculate that. So this object isn't moving, so if it's not moving, you know these forces have to balance. And so we can say that force buoyant is equal to Ft plus Fg. We can rearrange n for the tension force, and we can just start plugging in our values. And once we do that, we just start simplifying. Notice I got that volume via the dimensions of the briefcase, just multiplying those three up to get the meters cubed. So finally, we just have to make this a smaller number, that 1, make this 0.1, and make this 10 to the 2 so that we can subtract appropriately. We get 4.9 from that mathematics there, and multiply that by 10 to the 2, you get 490 newtons. So that is the tension force, and voila, there is your answer. Whew, okay, another question here. A 2-meter cubed object is placed in a jar full of water on top of a scale. Again, that's a huge object. The scale reads 1.1 times 10 to the 3 newtons. Which of the following elements most likely makes up the majority of this object? So, and then we have our densities here. So this is the question that essentially is asking you, you have a volume of a given object. What is the mass of that object that's in there? And then based on knowledge of the mass of that object, you can calculate the density of that object and then compare that to these densities here and say which is this density closest to, and that's what that object is most likely made of, or made mostly of. Okay, so let's draw our forces. We have the force of gravity downward, that's mg. You got the buoyant force upward, and then you have that contact force, that normal force upward, at equal and opposite force. Okay, so then we say force of gravity is the force buoyant plus the force of the newtons. Force of gravity is equal to force buoyant plus the normal force. The force buoyant is equal to rho v fluid g. We know what that volume is. It's 2 meters cubed. And so we plug in our values, and we find the force of buoyant is equal to 2 times 10 to the 4th. And that should be in newtons. Now what we do is we figure out what the force of gravity is, which is mg. So we say that's 2 times 10 to the 4 plus 0.1 times 10 to the 4. Where am I getting that 0.1 times 10 to the 4? Well, that's the normal force, and the normal force is equal to this. The normal force is equal to that, the apparent weight. And so the force of gravity then is equal to 2.1 times 10 to the 4, which gives us a mass of 2.1 times 10 to the 3 kilograms, which if you divide that by 2, you essentially get 10 to the 3 kilograms, which is closest to B, silver, that density. So again, I just want to emphasize here the difference between the apparent weight and the actual weight. So when you put this in a fluid, and this is actually will probably explain to you more understandably why the normal force is not equal to mg in this case. Think about this. The force of gravity is quite literally the force of gravity. It's downward. But the buoyant force is pushing this object upward. So the actual force being felt by the surface here is less than what it would be if it were without an air. Okay? So then the equal and opposite force, the normal force, is going to be less than mg in the case of it being in a fluid like water. Did that make sense? The contact force is less, so the normal force is less. Turns out that the normal force is equal to the apparent weight. And that's how we figured out what all these values were. Sit on it, deal with it. We'll keep moving on to the next question. Here's a more chemistry type question. Air is roughly 7 times as heavy as helium at a pressure of 1 atmosphere. A child named Robin is at a birthday party and is given a helium balloon. She accidentally lets the balloon go. If the temperature of the balloon does not change, the balloon will rise. And I'm going to go straight to the answer because I don't want to waste time, explaining each one here. D, until the pressure inside the balloon is 7 times greater than the pressure of the surrounding atmosphere. Okay. So here's the thing here. Here are the equations you need to know. Again, basically, you just need to know what's being held constant, as always. But people always get so tripped up about this. Okay, PV equals nRT. This is equal to what? M over V. Mass over unit volume. PV equals nRT. The temperature is being held constant. So PV is a constant. And, okay, if you increase pressure, what happens to volume? De facto, it decreases. And if the volume decreases, what happens to density? The density increases. When the density increases, when the density of helium increases to the equal to that of air, it stops moving. It stops rising. And so that's why the answer is D. Hopefully that makes sense. Again, you just need to know it's being held constant. No magic here. And we can move on then to moving fluids. Have fun. So I'm really going to give moving fluid a bit of a hand-waving treatment. Not because it's not important, important, but because we cover it in another lecture. So really, I'm just going to deal with the basic physics and introduce you to the equations you need to deal with moving fluids, and then later on we'll deal with it in the context of the cardiovascular system, which is where you would get most of your questions anyway. So when you're talking about a fluid moving, the molecules are moving, and even in a static fluid they're moving, but there's something extra going on when the fluid is in a macroscopic state in motion. There are two fluid movements you need to consider for the ideal fluid, which is the random translational motion, just like you see in the static fluid to the right here, and you also see that in moving fluid, and that's actually what generates the pressure on the walls of the container. And the uniform translational motion, that's the type of movement you see in moving fluids alone, and not in static fluids. So, in the name tells you what it is: uniform translational motion. So all the molecules moving in one direction. So, let's say you have the static fluid. What generates that movement to begin with? Well, in a static fluid, as you know, static fluids have a temperature associated with them, and if it's going to be a fluid, that means you're going to have some kinetic energy associated with it, some random kinetic energy. And so all these molecules are moving in random directions, and once you pop a hole into this little container, you're going to give them a pathway for them to flow down. And if the pressure in the fluid is higher than the pressure out there, which it is, it's going to flow down. And even if it And then again, what's producing that? Forget about mathematically, but what's producing that? Now suddenly the molecules are randomly moving, and this one happened to be going this way, and a bunch of them happened to be going this way when this thing cracked open, and so now you have a flow of fluid down. So forget about math. That's just why it happens. Now, ideal fluids have some properties associated with them that you should know. First is that they experience laminar flow or non-turbulent flow, smooth flow. So if you can imagine a picture of a fluid flowing down a slide, that would probably be laminar flow. What laminar flow is essentially just the flow of fluid in sheaths or layers, where each layer then interacting or bumping into the other layer. So it's just a very smooth flow. And turbulent flow would be, for example, if you have these fluid molecules flowing down to the right here and all in the same direction, and some random fluid molecule went here and bumped it, it would cause some turbulence. Ideal fluid, they're incompressible. They have no viscosity. So viscosity is thickness, viscosity, thickness. Example of a viscous fluid would be molasses, if you've ever seen a jar of molasses in your kitchen, or maybe even you can think of a very thick syrup or honey as a viscous fluid. Just a thick fluid, and then you can imagine that would slow down flow, or velocity of fluid flow rather. And the second thing is that ideal fluids have irrotational flow. So we just assume that these little water molecules here that I'm coloring in red aren't rotating about their axis, which under normal conditions they are, but ideal fluids they're not. And that's the ideal fluid. So now what we'll do is just discuss the different equations you're going to need to deal with the kind of questions you'll see in terms of ideal fluids. The first is the continuity equation. So continuity equation says that the flow Q is equal to the area of the pipe times the velocity of fluid flow, and that is a constant. That is not changing. That is equal to one another. So that just says that if you increase the area, you decrease the velocity. If you increase the velocity, you decrease the area, because flow rate has to stay constant. Flow rate has units of volumes per second. You can also express flow rate in mass per second, which that would just be then what? Well, it would be mass per second, so you just multiply by density to get rid of that volume there. But you more generally just see flow rate is equal to volumes per second. So again, the area here is greater than the area here. So this area that is smaller, if you decrease the area, you increase the velocity of fluid flow. Why don't we think about just for a second why that is the case? Forget about the equation for a second, but think about it. You've got fluid in here, right? And it's moving at some rate, some volume per second. If you were to, make this smaller, then if the flow rate wasn't constant, then you'd have a buildup of fluid here at this end and a less amount of fluid here at this end. But we know that just doesn't happen. I mean, that's not how this works. What happens is if you decrease the area of the pipe, this fluid just travels faster to get out of there more quickly. And so that's why flow rate is constant. And just to be clear, the value of flow rate can change, right? So this value can change, but the fact is that the flow rate here is going to be equal to the flow rate here. And the flow rate here is going to be equal to the flow rate here. Okay? That's what we mean by it's constant. That doesn't mean that, flow rate can't change from 5 liters per second to 4. All that means is to say that if if it changes from 5 liters per second to 4 liters per second, that's going to be system-wide, such that the flow rate at any one of these points in the pipe is going to be the same. And just while we're here, and just while we have this notion of velocity, the fastest the fluid is ever going to flow is going to be right at the center. Because at the sides, you have these resistive forces that can, like friction, that can slow down the fluid flow. But the fastest the fluid is ever going to flow is right in the middle. That's just something you should know. That's the continuity equation. Q is equal to A to V. Okay, now we have Bernoulli's equation. So Bernoulli's equation is essentially just a restatement of the conservation of energy using the terms that describe the intrinsic property of the fluids, that is, density and pressure. So here it is. P1, the pressure, 1, the static pressure, 1, plus the density of fluid times gravity times the height of the fluid, which is not the same as the depth, by the way. We'll cover that shortly. Plus 1/2 the density of the fluid times the velocity of that fluid squared is equal to those values at another point. So P1, let's say here, is equal to, well, all these three terms combined is equal to all these three terms combined on this other point. So why don't we go through some of these things. The first thing that I want to say before we cover anything else is that this rho GH is set as the h being an arbitrary height from some 0 point. This is the potential energy, if you would, and we'll cover that in a second. This is some height h from some arbitrary point down here. Some height h. It is not the depth, and that's what I think a lot of people get confused. The depth equation, rho GH, a gauge pressure, that's used for static fluids. And there are some cases where you need to use that equation to determine the static pressure. But again, you'll see that again will be used in static fluids only. Anyway, why don't we derive how this is conservation of energy? So you have this, and this is the more functional form. And that's what's called the piezometric head. We haven't covered these terms yet. Ignore this for a second. This is the more functional form. You can say, for example, if the height is constant, if velocity increases, pressure decreases, just mathematically from this equation. You can say if the velocity is constant and the height increases, you can say that the pressure has to decrease in order to keep this constant, right? So that's what Bernoulli's equation is useful for, and that's qualitatively what you need to understand. But just showing you how this is conservation of energy. If you multiply the terms here by volume, what you end up doing is you start canceling out some stuff. You cancel out the area on the red term, and on the green term you cancel out that volume, and on the purple term you cancel out that volume. And what you end up getting is kinetic energy random. This is just energy. Plus mgh, or the potential energy, plus 1/2 mv squared, the kinetic energy, is constant. So you notice there's two kinetic energy terms here. This kinetic energy term is referring to the random translational motion, and this one is referring to the uniform translational motion. All of those go into determining what kinetic energy is. And so that's why you see two terms there. But all this is just a statement of energy is conserved from one point to the next. All that is saying. And this is for ideal fluids, right? For a real fluid, you might have some friction or some viscosity or some drag or some turbulence that may dissipate this, but for an ideal fluid, this is going to be true. So now you hopefully can see why this is potential energy and kinetic energy and such. So there are some terms that we use to describe these terms. There's the pressure head, the elevation head, and the velocity head. I think the biggest mistake people make is that they assume that all of these are pressures. All of these things here have the units of pressure, but they're not the pressure that we're interested in when we say what is the pressure of this fluid. When we ask for the pressure of a fluid, we're talking about what is the force per unit area that this vessel wall is feeling by the water molecules, for example, hitting up on the side wall here. That is the pressure we're interested in. And so if you were to increase velocity, some of you might say that should increase pressure because now the water, if I put my face here, is going to hit me a lot harder, right? Like if I put my finger on the hose to decrease the area of the hose and hence increase the velocity of the fluid flow out, I would say that's an increased pressure, but that's not the pressure we're interested in. Yes, I agree with you. The pressure that you will feel when the water hits your face is going to hurt more. It's going to be a stronger pressure than if you hadn't covered it up with your hand. But that's not the pressure we're interested in. The pressure we are interested in is this pressure, the hydrostatic pressure, the pressure from the fluid molecules hitting on the sidewall here. Okay, so that's the pressure. These other things are not what we consider pressure. They have units of pressure, and they are pressures, but that's not the pressure we're interested in. This is the pressure. So hopefully that will help you to understand why increasing velocity will decrease pressure and height and what have you. And again, this is not the same as depth, and as we go through questions, it may be more apparent to you. But just to continue on here, if you decrease the area, you'll increase velocity. And that's represented, by the way, in a shift from random translational motion to uniform translational motion. So maybe this will help you understand even more so why this would end up decreasing area would increase velocity and decrease pressure. If you have an increase from random translational motion to uniform translational motion, you have more molecules just going straight like this, and less molecules hitting up on the sidewall of the vessel. And you have less molecules hitting up on the sidewall of the vessel, that's a decrease in pressure. Represented here, it's like saying, okay, you have an increased velocity, so you have a decreased random kinetic energy, you have a decrease in the random translational motion, and hence you'd have a decrease in pressure because the random translational motion is what's generating that pressure. If you have a decrease in height, you have an increase in pressure due to just conservation of energy. If we're looking at this term, if you're decreasing height, you're decreasing potential energy, and in order to keep this constant now, if velocity isn't changing because the area isn't changing, you're gonna have to increase the random kinetic energy or increase the pressure, which is this term here. You should use this by the way. You shouldn't be using this thing. You should really be using this to do this, and this is what you should memorize. Now by this, I mean Bernoulli's equation here. You should memorize this. And then the other thing that I want to mention here is that these truly aren't the pressure, elevation, and velocity head. If you really want those values, they're actually supposed to divide by rho times gravity. But for our purposes, we're just going to call these things the pressure, the elevation, and the velocity heads. Just moving on, let's go through some questions now. Suppose a fish tank of 82 meters high and filled with water is open to the atmosphere and is hit with a bullet that pierces one side of the tank, allowing the water to flow out. The hole is 2 meters above the ground. If the hole is very small in comparison with the size of the tank, how quickly will the water flow out of the tank? Okay, so this is the Bernoulli's equation question, and what we really need to do here is figure out that we need to use Bernoulli, and then just apply Bernoulli's equation to the situation. So we draw a diagram, and we try to figure out what these values are. Do we know what P1 is? It's the atmospheric pressure. This is open to the atmosphere, it's the atmospheric pressure. Do we know what V1 is? We do. Well, you may not know yet, but I'm going to tell you now. The convention is that you set V1 equal to 0 for a situation like this because we assume that the flow here is essentially close to 0. Is this moving? Yes. Is it moving very little? Yes. So we just assume it's 0. Now how about this? This is where we're interested. We want to find out what V2 is. We know what P2 is, isn't it? P2 is equal to atmospheric pressure because this is exposed to the atmosphere now. What's V2? Well, that's what we're interested in finding out. Are the heights changing? They are. So we need to account for that. So we plug in our value, then we know what rho GHs are because we have our values here at the heights of, you have a 2 meter and 82 meter high. So boom, we just kind of start rearranging Bernoulli's to ultimately get this equation here, and keep going until we find that V2 is equal to 2 square root of 2 times G times H. This is worth memorizing because this, you don't have time to do all this on the MCAT. You really don't. So this is worth memorizing. This will always work for you. You can just plug in to find out what that V final is, which ends up in this case to be 40 meters per second. Going on, a U-tube manometer containing water is connected to a nozzle of an air tunnel that empties into the atmosphere as shown below. The area ratio of A2 over A1 is equal to 0.25. In the given conditions, the height difference in the manometer is 100 millimeters. The density of air is 1.23 kilograms per meter cubed. What is the average air velocity at the nozzle exit V2? And you can leave it in the square root form. Okay, so we actually have a bit of a nuance here. We actually have a static fluid question and a moving fluid question. And so the static fluid in this case is this manometer here, and then the moving fluid here is this air tunnel. And so again, you already know just from your day-to-day experience that if the pressure here is higher than the pressure here, then this is going to push this fluid up, right? Pressure gradient. And so we can use that difference in height to determine what the pressure difference is between this point and this point. And guess what? The pressure here is equal to the pressure here because this is exposed to the atmosphere. And so we can use this height difference to determine the pressure difference between these 2 points, and then given the pressure difference between those 2 points, you can then determine what the velocity at V2 is. And we also have to use this area ratio to determine the relationship between V1 and V2. Anyway, we use Bernoulli's equation. We get rid of the height because the height isn't changing here. We assume that the small change in height here is not important. And now we have P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. And we could use Q is equal to AB to determine the relationship between V1 and V2. I found out that A1 is equal to 4 times A2 just from their area ratio. Just multiply this side by 2. You get A2 is equal to A1 0.25. So A2 divided by 0.25 is equal to A1, or A1 is equal to 4 times A2. So that means V2 is V2 over 4, which is equal to V1. We can plug in V2 over 4 for V1. And now we can rearrange this to show P1 minus P2 is equal to 1/2 rho V2 squared minus 0.25 V2 squared. Notice I took this out. So both of these had 1/2 rho multiplied by them. So I just kind of took that out and put it behind the parentheses here. All right, and I changed divide by 4 to 0.25. Anyway, this here is the gauge pressure. And we know what the gauge pressure is because we have this thing here. So we can figure out what that is. I'm sorry, I put this twice. P gauge is equal to rho water GH. And then the gauge pressure, again, is just these values that we have here. The density of water times 10 times height. Notice we're not using the density of air. The density of water because the water is what's in the manometer here. Okay, now we know what P1 minus P2 is. Now we just solve for V2. After some mathematics, you can find V2 is equal to 41.64 meters per second. Not too bad. Another question here. So the one thing about fluids is that you can be asked questions about fluid mechanics, moving fluids, in so many different iterations and variations that I can't show you all of them, but I'm trying to show you most of them. Mariano Rivera comes up to you and says, it's all in the flick of the wrist, right before you heard the curved ball as shown below. The blue arrow shows the direction of the ball's travel. The red arrow shows rotation. Which labeled pressure is the higher pressure? All right, so you have this ball moving in this direction, and so if that ball is moving in this direction, the air is moving in the opposite direction. The other way you can think about it, that from the perspective of the air, from the perspective of the ball, the air is moving. And so anyway, the velocity of air is going that way, and these are called stream lines, by the way. And the closer the stream lines, the faster the velocity of the air travel is, or the fluid travel. And the further apart they are, the slower it is, the less velocity it has. I probably won't ever mention that again, but probably worth noting. Anyway, this ball is rotating this way, and so in this direction, it's actually increasing the velocity of the fluid next to it, right? Because it's rotating and it's dragging the fluid along with it. So if you increase velocity, what's happening to pressure? Pressure decrease. So the pressure P2 is lower than P1. And if you look at this side, this velocity is decreasing because it's going against the air current flow. And if that velocity is decreasing, then the pressure increases. So P1 is greater than P2. There's a pressure gradient there, so the ball curves inward, and that's how you throw a curved ball. One of the issues that people always have is the different tubes that you can use in moving fluids to measure pressure, and what values do those tubes measure. So one of those tubes that people get confused over is the pitot tube. The pitot tube measures velocity and can compare pressure between static and moving fluids over short distances. So in the case of the pitot tube, the structure is you have one that is 90 degrees to the movement of the fluid. If it's 90 degrees to the movement of the fluid, it cannot measure the velocity head. It cannot measure this. If it's 90 degrees, all it's measuring is the static fluid, or the static pressure rather, or the pressure that's due to the random kinetic energy of the molecules. And that will then generate a pressure onto this tube that pushes this, in this case, fluid water, up this tube. Now, the pitot tube on the other end is in line with the movement of the fluid. So if you're in line with the movement of the fluid, you can get both the velocity head as a pressure that pushes this fluid up, and you can also get the static fluid pressure, because the static fluid pressure is generated from the random kinetic energy of the molecules moving in a random direction, which isn't just at the corner of, or which isn't just at the side of the vessel itself. So this gets both static and velocity head pressure. Now, if you know that that is the case, then the difference between these two pressures is going to be what? Well, it's going to be the gauge pressure. And that difference in pressure is just going to be due to the difference in pressure between point 1 and point 2. And so that information, if you know the gauge pressure, you can now calculate what V2 is, and that's why the pitot tube is useful. And I'll further illuminate that to you by breaking out this equation. First off, we know we're ignoring the height differences between these 2 points. We're saying that the arbitrary height between this point here and this point here is arbitrary in this case. Okay? Let's erase everything now. Let's just put point 1 and point 2 again. So boom. That allows, and then the next thing we say is that V1 is equal to 0, or the velocity here is equal to 0. Why am I saying that? I'm saying that because this is at a 90-degree angle from the movement of the fluid, which in this case is from left to right. This velocity here is referring to the uniform translational motion velocity, which in this case at P1 is going to be 0. Is there a velocity here? Yes, the random kinetic energy velocity. But that is not the velocity being referred to here. This is referring to uniform translational motion. That's why I'm able to say that's 0. Now we can rearrange this equation to say P1 minus P2 is equal to 1/2 rho A V2 squared, where rho A is the density of the air, which is the fluid moving in this case. It's important that you use the density of the air. Now what's P1 minus P2? Well, we've already determined that to be the difference in height in this fluid manometer here, or the pitot tube, whatever you want to call it. And so we use this. P1 minus P2 is equal to rho water G times height, or the gauge pressure. How come I'm using this static fluid thing for a moving fluid question? Well, this fluid is static. This is a static fluid, so we can use this equation to calculate that. This height, again, is not the same as rho GH in here. This is height and this is depth, really, or the difference in height between the 2 points. Anyway, how is this different from what I showed you earlier with the YouTube manometer? Well, let me show you why this is different. If we go back to that question, here we have a YouTube manometer, and we want to know what the final velocity here, V2, is. So we find out what the pressure here is using this static pressure tap, and it pushes the fluid up. And we want to find out what the pressure here is to be able to determine what V2 is. Now we know that since this is open to the atmosphere, that the pressure here is equal to the pressure here. So that's why we're able to use this YouTube manometer to determine the pressure difference between these 2 points. By figuring out the pressure difference between these 2 points because they were the same. But if the fluid is closed off and not open to the atmosphere, so the pipe just keeps going, you wouldn't have been able to do that because these pressures here would not have been equal. But with the manometer, you can determine what the pressure is here, but with the pitot tube, you can determine what the pressure is here, and then use that difference in pressure between those two to find that V2 velocity. And not necessarily in this case, but just in general. Hopefully that makes sense with the difference between the two. Let me move on. Moving on, the Venturi effect and Venturi meter. So this is nothing new to you. All the Venturi effect says is that if you have a lower velocity, you have a higher pressure. If you have a higher velocity, you have a lower pressure. All that comes down to the fact is that if you decrease the area, then you increase the velocity of fluid flow. You have more uniform translational motion and less random translational motion. Hence, you have less pressure when you lower area and hence increase velocity. That's all Venturi effect says. And what a Venturi meter is essentially a U-tube that takes the measures the pressure at different areas and hence allows you to calculate the velocity at different areas based on that pressure difference. Now, the Venturi meter, again, some of these tools are redundant, but the Venturi meter can be used when the pressure difference is pretty great, because if you try to use the Venturi meter between here and here, you wouldn't be able to do it. So if you wanted to know the velocity here versus the velocity here, well, clearly the velocity should be the same because the height hasn't changed, but let's just say superficially you wanted to do that, this Venturi meter wouldn't read anything, right? So usually the Venturi meter has to be used when the area differences are pretty great for you to be able to use it. Or if you wanted to, for example, if you wanted to figure out the pressure difference between here and here, the Venturi meter won't do you much good. Alright, so here's a figure that really puts everything together for us and really helps us to understand the difference between having a tube in line versus having a tube at a 90 degree from the fluid movement. So remember, pressure plus rho GH, the elevation head, plus 1/2 rho V squared, the velocity head is constant, or the piezometric head is constant. So here's the piezometer line, or the energy line, and you'll notice this yellow line doesn't change at all here. So we'll start out with complete potential energy, which is shown here as rho GH, this green arrow, and we'll go here and we'll see what happens as we change area or velocity or height and see what happens. So why don't we set our baseline? At baseline here, our first set of tubes we'll notice that we have some static pressure, some potential energy, and some kinetic energy. Alright, and as we convert from here to here, what changes? The height. The height increases. The area doesn't change, so the velocity doesn't change, so we'll notice that 1/2 rho v squared is the same on both positions here. However, since the height increased, if the height increases, the pressure should decrease, so we notice a decrease in static pressure represented by the smaller arrow here as compared to this arrow, or represented by the smaller volume of the tube. Okay, good. If we move from this point here now, this red point that I'm lining, to this one where the area has increased but the height hasn't changed, if the area increases by the continuity equation, the velocity decreases. So our velocity head should be decreased, which it is, represented by the small blue arrow, or represented by the smaller amount of volume of this tube. Notice that the piezometric tube gets both the static pressure and the velocity head. And so you'll notice that the static pressure now has increased because velocity has decreased, and then that takes up that much of the piezometric tube. And then the rest of this is due to the velocity of the fluid flow. Okay, moving right along here to the next junction where we have tubes, you'll notice that we've increased the height tremendously, and we decreased the area. So we've decreased the area, we've increased the velocity of fluid flow, so now we have a stronger velocity head. And the rho GH is increased because we've increased height. And now the pressure is so low that we would call this then a negative pressure. And it's not that the pressure is 0 or less than 0. That's not what the case is. When we call this a negative pressure, we're referring to a pressure difference such that the atmospheric pressure here in air is greater than the pressure in the tube here, and then that the static pressure tap will actually cause the fluid to flow into the air, to flow into this liquid, if this is water or whatever. Doesn't matter if it's water. So hopefully that helped us understand how these pipes will change in height depending on whether you increase area or decrease velocity or what have you. What we'll do next is we'll just look at real fluids for a second, and then we're going to end up the lecture then. Alright, real fluids. Real fluids follow Poiseuille's law. Poiseuille's law just said that delta P, the pressure gradient, is equal to flow times resistance to flow, where resistance is 8 eta L over pi r to the 4th power. Delta P, the pressure gradient, or the difference in pressure. Q is the flow, R is the resistance to flow. N is viscosity, L is the length of the pipe, and R is the radius of the pipe. So it just said that if you increase length, you're going to increase resistance, and if you increase resistance, if the flow is constant, you're going to increase pressure gradient. So we can go through each one of these variables, but I think you understand that, and we're going to go through this more on the next lecture, so I'm not going to make a big stink about this. The only big stink that I'm going to make in this lecture about real fluid is that there is a difference between a pressure gradient and absolute pressure. A lot of people get confused because they try to say, okay, well, Poiseuille's law says that if you increase the length, well, rather, if you decrease the radius of the pipe, which is decreasing the area, you're going to increase resistance, and if you increase resistance, you're going to increase pressure. And then they'll say, well, Bernoulli's equation says if you decrease area, you increase velocity, and you decrease pressure, so what's going on? You're applying this equation wrong. There is a difference between a pressure gradient and an absolute pressure. I'm going to make this very clear to you. Okay, let's say we have this pipe, and it does a constriction like this. Okay. The pressure here, well, let's get the constriction point. Let's just call this P1, and let's call this P2. The pressure here, the area has decreased, so the velocity increases. And if the velocity increased by Bernoulli's equation, the pressure decreases. So P2 is smaller than P1. So P1 here, if the area increases, the velocity decreases. If the velocity decreases, the pressure increases. So now if you say P1 minus P2, that's an increase, that's delta P, that's an increase in the pressure gradient. That's just what Poiseuille's law says. Poiseuille's law says if you decrease the area or the radius, you're going to increase the resistance, and if you increase the resistance, you're going to increase the pressure. See, there's nothing incoherent about Poiseuille's law and Bernoulli. You're just applying it wrong. So here's just another picture showing you that. And this is from fet.colorado.edu. That's some very good stuff. So if we do a little constriction, for example, we vasoconstrict our blood vessels, that would cause then what's called an increase in the pressure gradient, but that would actually cause a decrease in the pressure inside of that vessel. So notice 122 minus 103 caused an increase in the pressure gradient, but inside the vessel the pressure decreased and outside the vessel it increased. So hopefully that can help you to understand why the difference between absolute pressure and pressure gradients. Moving on here, turbulence. Turbulence is any pattern of fluid motion characterized by chaotic changes in pressure and flow velocity. As we already mentioned, if you imagine laminar flow, which is just all the molecules moving in one direction in little sheaths, none of them interacting or bumping into one another. If something comes along and bumps it, you're going to ruin the flow, and you're going to get turbulence or some vibratory motions or some hitting or some rough fluid movement or waves as these things hit each other and bounce off one another now. So as you go faster and faster, you know that you'll have bigger collision just based on, well, momentum, really. The faster you're going, the bigger the collision is going to be, and the more you'll repulse one another when you hit each other and bounce off one another, and hence the stronger the turbulence. So the faster you go, more turbulence. Moving on, surface tension and capillary action. Surface tension can be explained energetically and entropically. Surface tension is not the same as the buoyant force. Surface tension is, well, what you see right here. Here's this nice water strider right on top of the water. And how it's being able to stay on top of the water or walk on water without falling in is that there are hydrogen bonds between the water molecules at the top of the surface here that this water strider is not breaking by spreading out his weight with his really long legs. So it's not making a big pressure in any one point that would make him fall through. That surface tension is a result of the hydrogen bonds and a result of the fact that the water has to form these ordered water cages around the air, or try to form an ordered water cage around the air. And in order to minimize its contact with the air and hence maximize its entropy, or maximize the amount of microstates available to it. But it really just fails on doing that, and then the net result, for whatever reason, is that these water molecules on top here are relatively constrained to moving. And so now you have these hydrogen bonds constrained to moving, so the hydrogen bonds are not breaking or reforming, they're just kind of stagnant and constant. And so they form a permanent resistance there, and in the form of surface tension due to the hydrogen bonds between these puppies. And the net force, by the way, is inward. And how you know that to be the case, forget about trying to understand why the net force is inward. But you know that to be the case because when you put water in a hydrophobic environment, like on top of a hydrophobic leaf, you'll notice it forms a bead. And so the reason why that is, entropically anyway, is because it wants to minimize its contacts with the nonpolar substance in order to maximize its entropy. There are amphipathic molecules that can break up surface tension, and the way they do that is that they point. So amphipathic just means they have hydrophobic and hydrophilic ends. So they point their hydrophilic ends to the water and the hydrophobic ends to the air, allowing for then the movement of these molecules, and hence the breaking up of surface tension. Another way you can break up surface tension, for example, if you're falling out of a plane, is you might throw a bomb before you hit the water, so that it can blow up the surface of the water, and now hopefully you won't die when you hit the water, because now the water can only provide temporal resistance to you. In fact, that'll act as a cushion. Okay, moving on. Capillary action. So capillary action is the spontaneous flow of fluid into a small tube. It's not the same as what happens with like a piezometer tube or a static tap tube or a manometer. What's happening with capillary action is that there are attractive and cohesive forces that cause for the fluid to move up the tube. For example, in water, in glass is silicon dioxide, which is a polar molecule, and so the water is attracted to the glass, and so it moves up the glass tube. There's also the cohesive forces that from the intermolecular attraction in the fluid molecule that causes it to not go up the tube, and so that would then determine the height it goes up the tube. You'll notice that most of the fluid drawings that I did in this lecture, I drew a meniscus. So meniscus is just a curved surface of a fluid up a tube or container. And that's just showing you that fluid, if the meniscus is curved upward, that there's attractive forces between the fluid and the container that is greater than the cohesive forces. That is not the case with mercury, as shown here. The attractive force between the polar silicon dioxide glass here and the nonpolar mercury is causing that pull downward. And so you'll notice that this pull downward is not due to attractive force, but rather due to the cohesive attractive forces within the mercury itself. Capillary action has its relevance to medicine in that we usually use these very, very small glass tubes to collect blood samples, small blood samples from people. For example, people who are diabetic, you just have to have the blood glucose tested. And how they do that, they give themselves a little finger prick, and they take a little glass tube, and the glass tube is usually housed in a little machine, and then that pulls it up just by capillary action. Then you can test the blood for glucose. Anyway, the other thing to emphasize that capillary action only works in very small tubes. Okay, that's the end of the lecture. I hope you enjoyed it. Again, we're giving this whole notion of moving fluids a bit of a hand waving because we cover it in the cardiovascular system lectures. I hope you enjoyed this lecture. I certainly enjoyed making it for you. If you're looking for more great content, visit our website at mcatdisciples.com and see if this course might be right for you. And if it is, I look forward to helping you get a great score on the MCAT.